Hello, y'all, and welcome to the last bonding lesson of the year. Not the last lesson. I think we have total 6 more lessons left in that, and then we're done with the course. So today we're going to talk about the consequences of polarity, and polarities of molecules affect how they behave or interact with themselves and other molecules. And we're going to talk about two things that polarity affects. One is solubility, which is the ability to dissolve. So if you don't know what solubility is, I would write that. And then the second one, which some of you are very familiar with, is intermolecular forces, which is abbreviated IMF. I'm going to tell you during this video which slides to take a picture of after I finish the slides, so you really need to pay attention to know which slides you need to submit. This will probably end up also being either 2 or 3 videos because I have a 15-minute recording limit. So again, in order for water, and let me get my pen out, okay, it must either have full or partial charges on it, okay? And thus, the only compounds that dissolve in water are ionic, because these have ions, and polar, because these have partial charges. And nonpolar compounds, because they have no charges, so these have no charges, they don't dissolve well at all. However, and then for this one we're talking about in water, nonpolar compounds will dissolve well in other solvents. So, for example, hexane is a nonpolar liquid. If you put a nonpolar solid into hexane, which is a nonpolar liquid, it will dissolve in that liquid. The general rule, which is kind of an oversimplification, is like dissolves like. So things that are polar and ionic will dissolve in things that are polar, and things that are nonpolar will dissolve in things that are nonpolar. So this is an image of dissolving, or showing how dissolving happens. So here, again, this is a ionic compound. And remember, in this form, when it's not in water, it doesn't conduct electricity. And then what happens when you put it in the presence of water, it pulls the ions apart, and the partial negative of oxygen surrounds the cation. This is the cation. And the partial positive of hydrogen surround the anion, thus pulling the crystal lattice. This is called a crystal lattice, or it's locked in a crystal lattice here, apart. And when the ions can move, they're able to conduct electricity. But that is how dissolving works for ionic compounds. The water molecules pull apart the crystal lattice, or the attractive forces between the cation and the anion. So this slide, I would like you to take a picture of, and hopefully on this slide, in order to get credit for this slide, you need to summarize what I said on the slide. All right. So here, and again, what's missing here, by the way, and you can fill them all in if you want, are bonds. Like, I'm just not drawing the bonds. But everywhere there's a single bond. They're all sigma bonds, but there's a single bond between all the atoms. They're just missing. I don't know why. So it says, consider the following solubility data in water, and explain octantol and propanol in terms of molecular structure and intermolecular forces. Okay, so this molecule has an extreme long area of a nonpolar region. This is because carbon-hydrogen bonds are nonpolar. Because its region of nonpolar is very large, it barely dissolves in water. Its solubility is very low in water. Okay, this one here has a smaller region that's nonpolar. Remember, carbon-hydrogen bonds are nonpolar. This part of the molecule is very polar. So it dissolves a little bit more because its nonpolar region is smaller. Okay? Now this has even a smaller nonpolar region. And this is the polar region. Remember, this is a polar bond because oxygen is a very electronegative. So this dissolves almost completely. Okay? So the summary point here is the more nonpolar the molecule is, or the greater the nonpolar region, the less it will dissolve, and you need to know that carbon-hydrogen regions are nonpolar. So here we're going to arrange these in order of increasing solubility in water, And to do that, we need to draw them, so I'm going to do that quickly for us. So that's this guy. That's this one. Okay, so I drew the molecules. And again, this is going to be a little bit confusing, but these molecules are all polar to some extent. Okay, they're all not symmetrical. My pen is not working. They're all not symmetrical. So they're all polar. Okay? So the ones that will dissolve the most are the ones that are the most polar. And you might say, Miss, well, this one and this one, they're the same shape. But this one is much, much more polar because the electronegativity difference between N and H is very large. Remember, N is one of the very electronegative elements. Okay? And actually, the electronegativity difference between P and H, even though this is non-symmetrical, it is polar, but it's not that polar. This one is not very polar at all, because the electronegativity values between P and H are actually pretty close. So this is not very polar. And this is actually very polar. And always we mess up. Very polar. Now, this one is the confusing one, okay? Because it has a small non-polar region, okay? But it has a region that is very polar, okay? Any element, any bonds to hydrogen that are bonded to F, O, or N are very polar. So, but it has a non-polar region, okay? And again, the reason why this one is not very polar is because P, even though this is not symmetrical, P and H have electronegativity values that are kind of really close to each other. I think this one is 2.1, and this one is like 2.5 or something like that. They're very close to each other, so this bond is not very polar. So this molecule here is the most polar, okay? So this is the one that's going to dissolve the best. This molecule is the second most polar because even though it has a non-polar region, it has this very polar OH bond. Remember, if you have these elements bonded to hydrogen, it's a very polar situation. So this one will be the second most dissolvable. And then last but not least, we have these sort of polar, but again, the electronegativity difference is not that far apart. So this one will be able to dissolve the least. So I would like you to submit this slide as part of the ones that you need to submit for homework. So now, which of these structures will best dissolve in water? So again, here we're looking for the ones that are polar. So this one is non-polar, and the reason why it's non-polar is that it is symmetrical. Okay? Now this one is symmetrical as well. This is trigonal planar. Remember, these bonds should be up. So it is also symmetrical. And now it's between these two. Okay? And we need to figure out the difference between those two. So I just want to make sure why you know this is non-polar. So if you draw, whoa, as the pen messes up. Alright. If you draw this one, remember the bond should be going up. And doesn't matter, though a bond doesn't matter. But this is the trigonal planar structure. It's sp2 hybridized. And that is symmetrical. So now we're between B and D. And again, this would they would not ask this question on a multiple choice. I just stole these dot structures from a multiple choice. This was not the question. These are actually pretty close in the one that would dissolve the most. They wouldn't ask you this question, but again, the point is that the one that is the most polar, okay, will dissolve the best. So to answer this question, you would have to actually get electronegativity values. So N is 3.0, and I'm just looking these up on a table. Again, on the AP exam, it would be more obvious, but again, I just want to show you sort of the battle that's happening between polarity and dissolving. So this is also 4.0. And again, this structure, you might think that it's symmetrical, but the lone pair pushes it down, so it's not symmetrical. That's what this one looks like. Oh, extra lone pair. This should only be, this is an extra lone pair. Cross that out. And then sulfur is 2.5. And then oxygen is 3.5. So actually, these bonds are both actually the same amount of polarity. So the dipole moments are here and here. And this one has a dipole moment here and here. So it's pretty close about which one would dissolve the best. And to be honest, it's pretty close. I don't even know if you can answer this question. They're both pretty polar. And again, on the AP exam, they would give you all ones that are non-polar, and then make you choose the polar one. I would probably say that B is the most dissolvable in water, because it has sort of F, which is very electronegative. But you could also make an argument for this, because none of these dipole moments cancel, whereas 2 of these do. So again, either B or D would dissolve best in water, because they are about equally polar. Again, this was not an AP question. I just stole the dot structures from an AP question. The AP question actually asked which one would have the biggest bond angle, was the AP question here. And that would actually be this one, because they're 120 degrees. Okay. So, now we're going to talk about intermolecular forces. I am going to upload this video, because we're sort of changing gears. But again, the point is, okay, so let me summarize the main point. Let me go previous. The point is that, and I want you to write this down, okay, the point is the structures that best dissolve in water are the ones that are most polar, okay, or ionic. All ionic compounds dissolve well in water, except for the ones that are insoluble. So really, ionic ones that are the 6. Alright, I'm going to upload this video and then do the second part.